What I see.
I can see it.
Okay, we're good to go. Thanks so much, Jenna. Thanks so much to Sustainable Northwest. Thanks everyone for joining us. I am just thrilled to get to talk about basically my favorite thing, which is old growth in Oregon. I thought of this title for my presentation all by myself without help from anyone. I am just going to take 10 minutes to get us started, give you a visual tour that addresses a couple what I think are key issues. I'm going to distinguish between dry and moist old growth for whatever that's worth. I'm going to try and answer the question of the day, how old is dry old growth? And make a couple other points, which is that large does not equal old and that dry old growth is going places. In that last piece, I'll speculate just a little bit about the future of dry old growth. First of all, old growth, dry versus moist. Everyone who spent any time in the Pacific Northwest should recognize this type of seed. On the left is Ponderosa pine, 300 to 400-year-old Ponderosa pine in Eastern Oregon. On the right is 300 to 400-year-old Douglas fir in Western Oregon. Iconic tree species, very different productivity, average of about 500 tons per acre in that dry system. In contrast, the west side old growth is one of the most productive terrestrial ecosystems on Earth, often more than 3,000 tons of biomass per acre. For those who are wondering, that's equivalent to about 25,000 football players on a football field. Very high biomass stands. What we think we know about fire disturbance in these stands, I'm displaying for you. This mean fire return intervals of around 13 years in this Ponderosa pine system. Mean fire return intervals as long as 400 years in these moist old growth systems in Western Oregon. I downloaded this information from the internet, so you know that it's correct. I was trying to think of what I think are, characteristic of these two different types of old growth, moist old growth and dry old growth, and this is what I came up with. In these moister old growth systems, old trees realize their ecological potential as part of a late successional stand. Dry forest old growth, old trees realize their ecological potential as individuals or clumps. In moist old growth, the overstory makes the understory. In dry old growth, the understory makes the overstory, and I'll unpack that a little bit with some photos. Here you see a classic photo of west side Douglas fir, Western hemlock old growth. Tons of leaf area, tons of complex vertical structure. What's growing on the ground is what light is available to grow it. Another view of another classic Douglas fir, Western hemlock old growth system. Not a ton of understory in this system because, again, it associates such complex vertical structure. Note again that there's old trees here. That Douglas fir in the upper left-hand part of the photo is 400 years old, but it really realizes this ecological potential as being part of this complex vertical and horizontal structure. In contrast, 300 to 400-year-old Ponderosa pines, they realize their potential as individuals or clumps. There's a lot of light in this system, and so what's characteristic of this system in its natural fire and successional regime is really copious herbaceous fuel, grass fuel on the understory that entrains a chronic surface fire regime. Another view of what the understory of kind of a natural Ponderosa pine stand looks like. All too often these days, this is what old growth Ponderosa pine looks like. Some scattered legacy 300 or 400-year-old trees surrounded by infill of, in this case, Douglas fir that dates to when fire was excluded from these stands. In a lot of ways, what's happening is that we're forcing these dry old growth systems to be more like the moist old growth systems. This has consequences, as Andrew, Paul, and Kale will describe for you. How old is dry old growth? I wish that we were together. I'd take a poll of the audience. Here's my answer for you. I don't know. One of our best guesses is from Dendroecological, that is tree ring reconstructions of stands in Eastern Oregon. Here's what those reconstructions look like. We've got a dozen or so sites here On the y-axis is the date that trees were established. Each of those circles is a tree. The color of the tree is the species of the tree. The size of the little circle is the contemporary size of the tree. Those red lines are reconstructed fire events at all those sites. The thick red line is the date of the last fire. One way that we could tell you how old an old growth tree is simply that it's a tree that dates back before fire was excluded from these landscapes, which invariably happened between 1850 and 1900 in most dry old growth systems. If you buy that, an old growth tree is simply one that dates to before fire was excluded from the landscape, dates to a point before when this critical ecological process was excluded. Two points to make, and then I'm done. First of all, large does not equal old. Here's examples of pretty large Ponderosa pine, 33 inches and 35 inches in diameter. They're actually fairly young and that dated to after fire was excluded from this meadow system. Here's a Douglas fir, quite large, 28 inches diameter, again, pretty young. Here's again what so many of these dry old forest systems look like. Old 300 or 400-year-old Ponderosa pine, quite large grand fir in this case that are again pretty young. Final point I want to make, and Keala, Paul, and Andrew will put a finer point to this, is that dry old growth is going places. What you see today is not what you're going to have in the future. What the future holds is drought and insect mortality and mortality from fire. Here's one of our long-term research plots in Eastern Oregon, before and after fire. A cartoon to illustrate some of the potential destinations of dry old growth. Here's what a typical dry old growth stand looks like in Eastern Oregon. Grand fir, Douglas fir, Ponderosa pine, western larch. There are different severities of fire and insects that could occur in this stand. Here's some of the potential outcomes of fire disturbance in this stand. Here's the stand again, and different intensities of mechanical thinning that are possible. Trees get turned into stumps in different paces and tempos and time and space. It's a really good time now to turn it over to my colleague at Oregon State University, Andrew Merschel. I'll project once again my title, my name, my email. Questions or comments, please you all drop me a line. I'm eager to talk more about dry old growth. Andrew, introduce yourself, take it away. Thanks again, everybody.
Thanks very much, James. That was a really good introduction to the rest of the presentations. Just make sure this screen share works out.
Looking
everyone,
good. Oh wait,
okay.
You're in presenter view.
Okay. How's that?
Perfect.
Okay. So what I'm going to do is talk about fire and old trees in dry forests. So James has really given us a good definition, and both he and I have spent a lot of time reconstructing how dry forest developed with frequent fire and reconstructing those frequent fires so we can better understand how we get old trees. And I think it's important to again focus on trees, since in dry forests, as James pointed out, individual trees act as old growth. So an outline, I'm going to start by making sure everybody understands how we reconstruct fire and forest development history in dry forests. After I do that, I'm going to show you guys an example of historical fire frequency and extent in the landscape that is currently being burned by the bootleg fire. So we're going to get a good understanding of just how frequent and how large fires used to be in our dry forests. And The important point there to emphasize is how those fires contributed to both the development of old growth trees and their persistence over time. And so that'll be my wrap up there. So starting off, I use Dendroecology to learn about how these forests develop and how processes like fire influences that development. Dendroecology is simply taking wood samples from trees and using the annual growth rings to date different events like tree establishment and fire in the stand. So what we do is we start by collecting tree cores from live trees, and that gives us a barcode or signature of growth over time. And the difference in growth rings, that their width, whether they're skinny or thick rings, is dependent on climate. So there's this barcode that is universally present in the trees we're sampling. So we start with living trees by taking tree cores, and then we're able to build ourselves a barcode that allows us to date things back in time that perhaps been dead for quite some time. So just another example of that, these are 5 tree cores. These 2 dots on each of the tree cores show the year 1750. And now we're looking at our barcode to make sure that these are dated correctly. And you can see at each arrow, there's a very thin ring with very thin late wood at the year 1757. And so 1757 is a severe drought that allows us today to make sure that our tree rings are dated correctly. And once we've done that, we can go out and we can sample logs and snags that have long records of forest development and also have records of fire and understand how these forests were shaped by fire. So just a quick summary on how that's done here. What I'm showing you here is a cross section collected from a tree established in the early 1500s. It died in the late 1700s. And what you can see on this cross section are wounds created by fire. So here's a wound created by fire in 1710, 1729, and 1751. And so these fires were low severity fires that burned around this tree and made a small injury on it. And then the tree basically grew over these wounds. And that's how we have a record of fire. So now I'm going to move from the tree to a sample point. When we're doing this research, we make a grid of sample points, and at each sample point, we cut cross sections from several different trees to develop a composite record of fire. So on this graph, each line represents the fire record for an individual tree. And when the tick marks indicate fire. So this is a large fire in the year 1795 that is experienced by all the trees in the stand. So as I said, I was going to summarize the fire history for the landscape that's now being burned by the bootleg fire. This is a fire history reconstruction I did in that landscape. The figure here on the left is showing you the study area and its outline. And then these different diamonds that are red are my sample points. And so each one of these sample points, I created a record of historical fires to understand how frequent fires were and how that varied across the landscape, and then also how large fires were. So today, the bootleg fire has burned basically from this point over and off the map, just for some context here. So at each one of these points, I'm developing a fire record, and now I'm going to summarize that pattern of fire across this landscape. On this graph, each individual line represents a fire record of a plot. So this is a plot, and this is a plot, and each tick mark is a fire at that plot. And if you look up and down this graph, you see that a lot of these tick marks line up in time. And what that tells us is that these were very big fires. So in 1795, there's a very large fire that burns across a huge portion of the study area. Same thing happens in 1822 and 1829. So just a representation of historical fire sizes in this landscape and their frequency. And that's on the top of this graph here on the right. What you're seeing is that in 1741, 1783, 1795, and so on, there were fires in this landscape that were over 100,000 acres. fires. So these are very large fire events. They're burning across different forest types. They're all dry forest types, but it's moving across them. And there's a ton of fire historically in this landscape. The bottom of this figure just gives you an idea of some of the spatial patterns of these fires. So any place that is red experienced the fire in 1795, and then areas in gray are areas where I didn't find evidence of that fire. But the main takeaway here is that large and extensive fires were frequent in these dry forest landscapes historically. Just one other summary point I want to make here. These big historical fires happen in years of severe drought. So the mean PDSI, which is a drought index, was negative 4.7 for my really large fire years in this study. And that's consistent with severe drought conditions that we're experiencing today. So historical fires happened in severe drought, just like today's fires. The difference about today's fires is that they're burning with much higher severity and killing a much greater proportion of our old growth trees than they did historically. And I think both Paul and Keala will help follow up with some data on that message. So I wanted to give everybody an idea of how extensively we've looked at the history of fire in Ponderosa pine forests in Oregon and Washington. This is an area that we actually have quite a bit of data, and we're real comfortable with how frequent and important fire was in these forests. The background of this map is showing you guys the range of Ponderosa pine, and it includes forests where Ponderosa pine is rare, so our very dry Eastside forest, and forests where Ponderosa pine is mixed with other species like grand fir, Douglas fir. So this covers dry to moist forests. Now I've put the different fire history reconstructions up on this map, and you can see that they're pretty extensive. We have a lot of data across the region in Ponderosa pine forests. And now I'm going to show you the different fire records at each of these sites. So this graph is picking out individual sites from the map on the left and showing you the pattern of fire there historically. I'm going to just show you one major point here, is that the effects of fire exclusion, like James said, were well underway by the early 20th century. Whether we're in relatively moist forest throughout the range of Ponderosa pine or dry forest, fire was excluded, and it had a big impact on these ecosystems by the end of the 19th century. So hopefully everybody can just see the degree to which we've removed fire. So I wanted to follow up with a little bit of discussion on what all this fire did and why it was important to our old growth trees. And so I have an example here from an old growth forest on the Deschutes. The forest I'm talking about is in the picture above, and in the graph below, I'm showing you the fire and establishment history of this forest. Each individual blue line on this graph shows the lifespan of a tree. And the vertical lines, again, indicate fires that happened as the stand developed. And what you can see is that this is an all-aged or many-age stand. It's old growth for dry forests, but there's many different tree ages, and there's been almost continuous establishment as low-severity fires repeatedly burn through this forest. And so that's very different than what we expect in our moist forests. And I think it's important to understand that what frequent low severity fire was doing is it's creating fine scale heterogeneity in tree ages, and it's maintaining our populations of old trees. So our old trees were historically surviving these regular fires. So just a visual on the heterogeneity that I was talking about. Our old forests aren't uniform stands of trees that are all the same age and growing up at the same time. They're actually collections of individual trees, clumps of trees, and open areas. So they have this very fine scale structure where you find individual trees, clumps, and open areas. And that's how old growth was structured historically with these frequent fires. And that's very important to these trees withstanding fire and other disturbances as they stay old and persist on the site. So what I'm trying to convey here is that we really didn't have stands like we do in our west side forest, where we have an even-aged group of trees growing up and going through succession and developing. What we really have is all of our different tree ages and size classes, snags and logs in more of an intimate mixture occurring in a much smaller area in our dry old forests. And so this is really important to these forests being resistant to disturbances like fire, drought, insects, and disease. And so just an illustration of how that works for fire. Our structure in these forests with frequent fire was very low density. Many of the trees were large and fire resistant trees. As I mentioned, there weren't stands, and these stands were constantly in flux. We had tree mortality and new trees establishing at a fine scale process rather than over really large, broad areas. And so I guess the message I'm trying to emphasize here is the scale at which resistance operated in this system. And it operated, within a stand because of this fine scale heterogeneity. Now just a graphic on what happens when we lose that fine scale heterogeneity. So this is our historical old growth condition. We remove fire as a process that creates that heterogeneity, and we get more homogeneous stands with more continuous fuels, and we lose the resistance that forest had. In a lot of cases, we also logged out our large and old trees, and that further removes the resistance of these stands to wildfire as they become loaded with smaller trees at a much higher density. So the removal of fire is a really big issue facing our old trees going forward. Just to wrap up here, I think Kiala and Paul will talk about this message more, but this is an image of the landscape where I did my fire history reconstruction and found that the landscape was tended by very large and frequent fires. Kiala is going to show you how that forest was structured historically and how it's changed in the past 100 years. And then, of course, this summer, that same area has been burned by the Bootleg fire. And so this is the imagery before that fire, and this is the imagery after that fire. And what we're seeing is a really, really dramatic and alarming change in how this forest burned compared to how it historically burned. So Kiala will have some more examples of what it looked like and how it survived fire before. But the outcome from the Bootleg fire is much, much different than what we would have seen historically. And a lot of that is due to the removal of frequent fire from this landscape. So just to wrap up, our dry forests were more prepared for disturbances that are going to be exacerbated or made worse by climate change in 1900 than they are today. We've moved in the wrong direction in terms of climate change adaptation. When we have droughts and climate change today, those things are acting like catalysts for large changes in these ecosystems. They're making fire more likely. And when those fires are happening, they're going to have bigger impacts on our old growth trees. I think it's really important to realize that we can't stop some of these changes from happening. They're here and they're happening now. One thing that we can address is restoring fire as a process that's going to remove fuels from these ecosystems and help us protect and recruit old growth trees in the future. But as events like the Bootleg fire happen, I'm more and more convinced that we're running out of time and we need a lot of urgency in restoring fire to these landscapes. So that's the end of my presentation, and I will hand it over to Kiala.
Okay, well, to repeat, let me see if I'm sharing the right screen. I hope I am. To repeat, James's thank you to all of you for attending and to Sustainable Northwest for organizing this, and kudos to both James and Andrew for setting us up so well. I think I'm preaching to the choir when I talk to this group and say that these old growth tree populations have high social and ecological value, and has already been alluded to by both Andrew and James. We're potentially seeing an alarming decrease in old growth tree populations in some areas, at least, if not all. So I have had the good fortune of working around these trees for the last while. On 2 landscapes in Eastern Oregon, the Warm Springs Indian Reservation, which is southeast of Mount Hood, and the Klamath Reservation Forest, which is southeast of Crater Lake. So these color maps show us the vegetation types that we expect to find in the absence of fire or the absence of disturbance. On the Warm Springs on the left, if you move east across the landscape, you're moving down from the crest of the Cascade Range and into the shrub steppe. So you're moving from cold, wet forest down into the hot, dry Ponderosa pine through a band of mixed conifer. On the Klamath Reservation, it's a landscape dominated by Ponderosa pine with mixed conifer at higher elevations, and with lodgepole at both low elevation in cold air drainage area pockets and high elevation, like you can see here on Mount Yamsey near the upper tree line. So I've been working with 100-year-old timber inventory records on these 2 landscapes, and we found that on the left there you can see an example of one of the paper records that we found at the National Archives in Seattle. And these people, like these gentlemen shown here, or their forebears, cruised 20% of the area over 1.3 million acres on these 2 reservations combined. And as they did it, they tallied the number of trees by species and size class on 4-acre strips. So using that record and more recent records, we can look at the change in large trees over time. We don't have age data, but as James alluded to, size and age are not directly correlated, but data sets show that many trees larger than 21 inches in diameter are older than 150 years. So we've been on this landscape and have seen some of these great old trees. Anyway, diving in. The color breaks, the yellow shows where there were no large trees on the landscape, and the dark blue shows where the most abundant large trees were found. In the left column, it's the early 1900s. In the middle, it's 1985, and we see in the change in the color distribution, we see the change in large tree populations, largely as a result of selection harvesting. And then our harvesting of old growth trees was stopped on this landscape in the 1980s. And as has happened on other landscapes, we see more trees recruiting into the large tree size class under those since the late 20th century. Then, as Andrew alluded to, the bootleg fire happened this summer. And this photo I downloaded from InstaWeb. It was taken on July 26th within the footprint of the bootleg fire. And this is hazard tree removal. And you can see from the bark plates on this collection, this cluster of old trees, that those are really old trees, like over 300 years old. As Andrew said, the bootleg fire spread out from the southeast slopes of Fuego Mountain. This is the first day of the fire, and all the green shows the live vegetation. This orange here is the footprint of the bootleg fire as it moved out from the reservation forest, moved out from Mount Fuego. And taking a closer look, you've already seen it once before, but you can see in the change of the amount of green within the footprint of the fire that there's been a lot of mortality in that area. And we know from looking at the maps of old growth of large trees that there were some old trees in the fire. This is a photograph that Norm Johnson took of some of the fantastic old Ponderosa pines on the Klamath Reservation Forest. Unfortunately, this stand of trees is right outside the bootleg fire perimeter at the moment. So as Andrew alluded to, the accumulation of fuels over the past century of unprecedented fire exclusion is contributing to the way contemporary fires are burning at high intensity. And what this slide shows is the progression of increase in canopy cover over time. On the left, again, we have the 1920s, and yellow shows low values, dark blue shows high values. And you can see as you move through the late 20th century and into the early 21st century, canopy cover is increasing until in this area, the bootleg fire occurs. These red hatched areas are fires that happened prior to 2017. To reiterate, because I think it's so important, when I reiterate Andrew's point that before 1918, in the 200 years before 1918, there were at least 7 fire years that burned hundreds of thousands of acres during extreme drought. And in the 1918 fire, we have newspaper accounts and we have Bureau of Indian Affairs records documenting the fire, documenting the fire behavior, documenting the fire weather, and the footprint of the fire. And in the timber inventory records following that fire event in 1918, which was focused up here, most of the area has large old trees surviving after the fire. This is lodgepole pine flat up here in the northwest corner. So switching now to the Warm Springs reservation here, again, just a reminder, this is Mount Jefferson here, and it's the Klamath reservation that we were just looking at is in the east foothills, east of the Cascade Range, and the Warm Springs actually runs right up and over the Cascade Crest, and it has that strong band of mixed conifer. We have the same timber inventory records from the early 20th century for this landscape. And we see basically the same forest types, except that, or the same forest structures in terms of low density, open canopy dominated by large trees. But on this landscape, which is north of the Central Oregon Pumice Plateau, Douglas fir becomes a major component of mixed conifer forests in these forests, and 30% of the basal area in mixed conifer is in Douglas fir, with the rest dominated by Ponderosa pine. And that's what I'm showing on this slide. The color breaks here show the area where large Ponderosa pine, larger than 21 inches in diameter, dominated basal area, that's the blue, or contributed to basal area, that's the green, or there were no Ponderosa pine, that's the yellow. And again, oh, I haven't shown you that yet. These yellow pockets down here are where there was high severity fire, but I haven't shown you that yet. And I'm comparing this, I'm showing this side by side with the 1930s map of that the Forest Service produced for Oregon and Washington, where these color breaks indicate timber classifications based on species and tree size, large and small. These two orange shades here, the light orange and the darker orange, are Ponderosa pine forests that were dominated. Ponderosa pine are areas in which the timber was dominated by large Ponderosa pine. And I think these two maps complement each other well. It's just a suggestion that maybe in areas where you don't have the kind of historical data that Andrew was showing, or these early timber inventory records or other records of historical forest structure, the 1930s map might give you some information about what those conditions were like early in the era of fire exclusion. So what we did for both of these landscapes, but I'm going to focus on the Warm Spring, is we looked for all the early maps of high severity burns that we could find and so early in, we have these 5 different maps from early in the period of fire exclusion that documented high severity burns. Their definition of high severity is not the one we use today, but these are areas where most of the timber was killed during recent fire events. Looking at that map, then here on the left is the early 20th century, and the red indicates the red indicates the high severity burn patches from each of those 5 maps. And you can see that most of the large high severity patches were in the cold, wet forest types approaching the crest of the Cascade, with smaller patches and fewer patches as you move into the mixed conifer potential vegetation type, and almost nothing in the hot, dry Ponderosa pine dominated for, hot, dry Ponderosa pine vegetation types. On the right, we have the distribution of high severity fire in late 20th century, early 21st century fires. And you can see that high severity burns are distributed across vegetation types almost evenly. So we're getting more large high severity fire patches in the drier forest types and less in the colder forest types. However, this is 2016. It's before last year's Labor Day fires, which burned over quite a bit of the southwest quadrant of the Warm Springs Reservation. Switching gears slightly, I'm still showing the timber inventory map from the 1920s here on the left, but I'm showing now trees larger than 16 inches in diameter. And so all the blue area and green area is where there were trees larger than 16 inches recorded in those 4-acre transects. The yellow acres are where there were high severity burns in early 20th century records. And then on the right, this is another data set that Paul Hesberg will talk about and he has used extensively. It's based on the interpretation of aerial photography. Here in the middle, this is mid-20th century conditions, and on this landscape, extensive commercial harvesting didn't happen until the 1940s. So up until the mid-20th century, there were still large patches in which the overstory was dominated by medium and large trees. As a result of harvesting, these patches have been fragmented, and as a result of recent fires, as I've just shown you on previous maps, we're seeing a lot of loss of forest and creation of non-forest conditions. And that is a great segue to Paul. I'll just flash this slide up briefly to make the point that this work has been supported by numerous people who've contributed their extensive knowledge of these systems, who've contributed to data entry, data processing, and who've contributed funding to support these efforts. And that's it for me for now. So Paul, I will try to stop sharing this. Let's see. Okay, stop share. Great.
Thanks, Kala. And thanks to all of you for the marvelous setup and for being here this afternoon when you have other choices. I'm in cleanup position, and I think my assignment is to put some of these changes in conditions in a larger landscape context and in a fire and climate resilience context. So I will share my screen here. Let's see. And away we go. All right, my assignment is to look at threats and options for protecting old trees in fire excluded landscapes. And that's exactly what I'm going to do. This is a quick synopsis of the ground that I'm going to cover in my comments. When we look at very large landscapes, local, regional, provincial landscapes, we see that medium and large size mature and older trees were historically quite abundant. And fire exclusion over 150 plus years radically altered forests and woodlands that had these large trees. I'm going to discuss options for protecting remaining mature and old fire tolerant trees and recommend in some of my closing comments that there's a strong need to regrow trees into this condition because they're fire and highly climate adapted. I want to begin by looking at some data for 5 different provinces: the northern and southern Cascades, the upper Klamath country, which Andrew and Kala have spoken to, the northern glaciated mountains, and then this big Blue Mountains province, where we have sampled early and late 20th century conditions. And I want to focus attention on some of the findings from the Columbia Basin work. One of the things that we found out in these highly fire-prone areas is that very large patches of old multi and single-story forest occupied the landscape in these percentages. So there was quite a span, quite a difference, and a lot of that was driven by unique characteristics of the fire regime. For example, the northern glaciated mountains, it's dominated by a lot of moderate severity fire, and on the more extreme end of moderate severity. So it's very difficult for old forest patches to get indeed old and to occupy big space. However, when we look at the percentage of province area, same 5 provinces that had medium and large size older trees, what we find is that the percentage of the forest and the woodland area has extensive area in medium and large size trees. And so these are remnant canopy covers that are typically less than 24% of the total canopy cover. But what we notice is that many successional conditions have age in them. They have large structure, they have large snags, they have large down logs. And so essentially you have varied successional conditions with aging. But we know that there's a ton of changes to some of these landscapes, and I'm going to highlight them really briefly because they become really relevant to how we maintain and develop larger populations of these older trees on landscapes that are no longer fire and climate adapted. We can see that over the 20th and early 21st centuries, a lot of our dry slopes and ridgetops have filled in with trees, and many areas had these more sparsely wooded conditions or were covered with trees on the drier aspects and on the ridge locations with populations of medium and large sized trees that were highly fire tolerant. You can see significant change in those conditions in the 21st century. Similarly, in the moist mixed conifer forest, we see that there were areas that were influenced by moderate and high severity fires and a resulting very significant patchiness that was common on that landscape. And that varied age and density patchwork was really important to influencing fire flow of future fires, not only how big they got, but how severe they got. And we can see now uniform tree coverage. And in the interval between fires, which has been quite long now, you can see mountain pine beetle and Doug fir beetle filling in and creating mortality, fairly large patches. Further up in the colder forests, you can see that patches of burned and recovering forest were really quite common on that landscape. And over the last century or more, you can see continuous forest obtaining and making the landscape fairly contagious for high canopy cover, high canopy bulk density, surface fuels, so high likelihood of very large crown fires in these conditions. And a lot has been written about the primary change agents over this pre-1850 to modern era, and the usual suspects are logging of the large old trees, often the most fire tolerant trees, loss of indigenous burning, domestic livestock grazing, development of the built environment, ag development, fire suppression. These things kept fire out of the woods for a very long period. And then you couple that with a warmer, drier, now often windier climate, and these circumstances are escalating rapidly. So the question becomes, what are the threats to large and old trees in the 21st century in this context? The primary threat is a loss of large-scale forest landscape resilience. We have dense and layered forests, they're abundant. We have a high abundance of fire-intolerant trees, which I'll show you some data on further down the road. And these conditions together are promoting across very large landscapes, large severe wildfires, more severe than would be characteristic for many types, density-dependent drought mortality, density and climate-dependent bark beetle mortality, and then mixes of these things are also occurring. And much has been written and said about what sort of options we've had, and all of the speakers before me have discussed historical conditions and changes to them. And the primary factor that I'm going to highlight is that there's a loss of climate and wildfire resilient landscapes at very large scales, and there's an opportunity to adapt current conditions and improve their resistance and resilience to fire, drought, and advancing effects of climate change. We know there are a variety of conditions that are useful to, or tools that are useful to doing that, and they're best matched to the circumstance. We have opportunity to resume indigenous burning practices, do regular maintenance burning, and increase the coverage of medium and large old trees in most forest structural conditions. Here's a delightful chronosequence from Alan Tepley and Sharon Hood and others from 2020 EcoApps paper, showing a sequence of treatments in black bark Ponderosa pine stands. In these particular conditions, most of the large trees were removed, but you can see here after IPS and other bark beetle mortality in these stands, a sequence of burning and thinning that went on over 25 years to create, in a fairly short time interval, now highly resilient stand conditions favoring the larger size classes and recruitment into those future medium and large tree size classes. So thinning and burning work, and there's a lot of evidence to that effect. And the thinning and burning is an important thing, and it's much debated right now. In a paper that's coming out soon in Frontiers, we show the last 30 years of forest inventory and analysis results. In the top graph here, we're showing basal area per hectare changes, and in the bottom, trees per hectare changes. And the changes are set here relative to 1995 inventory conditions. And the DBH classes here are midpoints. These are the midpoints for the inventory years, and the DBH class midpoints are shown here as well. And what I want to show you is that there's significant increase in both trees and basal area, primarily in the Douglas fir, shown in this beige or sandy color, and the white fir and grand fir size classes that are shown here in this color. And so the increments of change are primarily occurring under those stand conditions, and they're occurring in quite substantially large diameter classes. There's also been quite a bit of discussion about vulnerability of the remaining populations of medium and large trees across the landscape. Here you can see a photo of a raked tree where the duff and litter accumulations were quite significant before treatment. And here you can see where those duff and litter accumulations have been left unraked. And the Noonan, Wright, and Fowler work here that I referenced suggests that under most circumstances, raking isn't necessary unless the caching of duff and litter accumulations is particularly large. So there's a real opportunity to do that burning underneath with methods that are useful to retaining those trees, and in most cases, the raking is not required. There are also really important relationships between some of the clumped and gapped conditions that Andrew and James referred to, which you can see here. This comes from Churchill et al., their 2013 paper, where they talk about the science behind spatially clumped and gapped tree conditions. And here you can see in Churchill et al.'s ICO implementation guide, marking that occurred within this patch to take the current growing stock and recreate clumped and gapped distributions that simulate the kinds of conditions that he and Larson and others in California have consistently discovered are consistent with the conditions of frequent fire forest. And this changes the way fire can behave by changing canopy bulk density, tree size class conditions, and the effect of flame length in creating crown fire initiation and spread conditions, basically dampening that likelihood. We're also finding through recent research that non-forests are a vital ingredient to resilient forested landscapes. And just for grins, I included this old Osborne panorama here. It's looking north on the Sayuthwa from Mary's Peak, which is west of Corvallis, Oregon. And this is from 1937. And you may think that non-forest patches, grassy balds, wet and dry meadows, shrub fields, those kinds of things are just unique to the fire ecology of the east side. But you can see here for hundreds of square miles, these south aspects that are staring back at us in the ridgetops basically were open canopy conditions and grass balds, meadows, if you will. And so this restoring resilience takes place in a larger context than just big trees and old forests and remnant large trees. The landscape of forest and non-forest is critical as well. Non-forest conditions occur as bare ground after fires, wet and dry meadows, shrublands, sparse woodlands and savannas, new stand initiation forest, and obviously mixes of these. And these non-forest conditions we're finding occur actually more frequently on forest-capable sites than on sites that are not capable of forest productivity, and they result after severe fires and most especially after reburns. And one of the things that we're finding out is that the complexity of many of these forest conditions that have an active fire regime, it comes out of reburning, fire-on-fire interactions over big space and time. These non-forest states can persist from decades to centuries, and they're often maintained by fire. Short persistence, several researchers are showing, are associated with smaller patches and lesser severities. Longer persistent, much larger patches, high severity. And these trade-offs are influenced by seed dispersal distances, climate and weather during the establishment period, which is a very vulnerable period for many coniferous species, and then the reburning frequency, which we're finding is also escalating now. So this vital context to forests provided by non-forest conditions is a key area to emphasize. Provinces vary in how much potential energy they can store as forest, and this is based on typical climatic conditions, the severe variability in climatic conditions, and essentially you can think of this forest, non-forest patchwork as representing the tug-of-war between factors that grow forest and factors that remove them via disturbance. Non-forest ends up being a fairly benign fire delivery system, so at some point in time you'll see systems tip back to more benign fire behavior at very large landscape scales. And as more and more forests obtain and they get denser, you'll see burning happen again, more non-forest created. And these forest non-forest relations appear to be in flux with changes in the climate and the weather. And these give us clues to what we can expect with climate change. We're expecting warmer and drier conditions, and that portends from our modeling that we can expect less forested area and more area with lower canopy cover. And in these particular circumstances, favoring medium and large size fire tolerant trees is a really important concept to carry forward. Regardless, the natural carrying capacity of forests is seldom realized in the historical fire ecology and the ecology of active fire regimes. I want to close with a refresher on some of the landscape restoration and adaptation principles, because I think they're really key context to talking about how we develop and maintain large tree populations on the landscape. We're coming to understand that the large-scale patchwork of forested areas, shrublands, sparse woodlands, grassland areas is a really key feature of resilient landscapes. So at each one of these scales, from broad to fine, all the way to tree clump and gap patterns within patches, it's critical that resilient characteristics are expressed at each scale of observation. The topography provides a natural template for adapting vegetation and habitat patterns. So we have the opportunity to actually use patterns of topographic facets as a means of tailoring more characteristic forest age, species, density, and life form patterns back to the landscape. Interactions between fire disturbances and other disturbance, these forest, non-forest successional patchworks and the climate, they're the combined engine that drives the system. And if we create supportive life form and forest successional and field patterns, we can adapt the fire regime so that an active fire regime can work for us rather than against us. And of course, the climate will continue to adapt these patterns. Predictable patch size distributions come from these topographic facets. In fact, when we look at historical patch sizes of successional conditions and patch distributions of topographic facets from ecoregion to ecoregion, they're statistically inseparable from each other. So using the topographic template is really useful for retailoring conditions back to the landscape in these patch size distributions that represent an active fire regime. And here you can see the transition between pre-suppression and suppression patch size distributions of fires and of resulting patches of forest structure and non-forest. Widely distributed large and old trees provide a critical backbone to these landscapes. They're climate and wildfire adapted, and they're a great way to store genes in a widespread way across the landscape. And the recommendation here is simply to keep more of them, keep what you have, and to make more of them. Finally, we talk about these successional patches as being basically small landscapes within the larger landscape. If you look at the patchy gappy patterns that are associated with the ICO patterns that all of these investigators have found in dry and now moist mixed conifer forest, these are very, very useful to influencing patch scale and patch neighborhood fire behavior. And so they're a critical building block at the lower level to creating resilience within these different pine, interior Douglas fir, dry and moist mixed conifer patches. And finally, if we're going to plan to do climate and wildfire adaptive treatments, the land lines across varied ownerships are troubling to be able to get the kinds of ecological treatments that really make sense across land lines. And so there's a huge opportunity to work collaboratively across land tenures to not only plan, but then implement projects. And now there's some policies within federal public land management to make that easier to do. Some key takeaways I'd like to summarize here. Medium and large sized trees were abundant historically. They occur in dry, moist, and cold forests. Old forests in fire-prone areas were less abundant. And these larger trees are most abundant in pine, dry, and moist mixed conifer forest. Sparse woodlands were less abundant, but they were also dominated by medium and large sized trees that were old in very low canopy cover conditions. We know that large logging targeted these trees in forests and in woodlands, and so they're much less abundant than they were. Fire exclusion over the last 150 to 170 years has radically changed these conditions. There have been continuous pulses of tree regeneration, which have been aptly shown by my colleagues, and forested area has increased. A lot of historical non-forest have been invaded by forests because they're capable of supporting forest growth. So forests got dense and layered, a lot of infilling of the shade-tolerant species, and also significant accumulation of woody surface fuels. So the setup is for large and severe fires. And as was mentioned earlier, large fires is not newsworthy, but the fact that they're consistently large and very often severe, those wildfires are providing a very blunt tool in terms of readapting the landscape. And so something else is really needed on the landscape. There's a lot of options for creating and protecting mature and old fire intolerant trees. One of the keys is restoring the larger landscape and making it fire and climate resilient. We can use solid landscape principles to do that. It's going to be a key to removing accumulated understory trees via thinning and burning and other tools that have accumulated during that long period of fire exclusion. And there's going to be a need to continuously prescribe burn accumulating woody surface fuels to maintain those conditions. There's a need to use appropriately managed wildfires as an additional tool in the toolbox. And there's a need to grow more fire-tolerant tree species into the larger size classes in open canopy arrangements that are going to be wildfire and climate change adapted. And with that, I will stop my formal remarks. And Jenna, I think this is an opportunity for Q&A to all the speakers. Is that right?
Yes, I've got a couple questions queued up already that might have been answered over the course of the presentation. But just a reminder, if you have additional questions for one or all of the panelists, you can go ahead and drop those in the chat. To start things off, I think this is a question for Andrew. How often did severe drought and fires typically happen compared to less severe fires, or something you might talk about for a fire return interval?
Sure, that's a great question. So usually about 4 times a century in some of these larger fire reconstructions, you see a really large and more extensive wildfire year that corresponds to a severe drought. So that's about 4 times a century. And in between that, you have lots of other wildfires that might be a little bit smaller. So it's not just small wildfires, it's also big wildfires that were contributing to the fire frequency in that landscape to result in really high frequency.
Great. I've got a couple of questions that have to do with spacing. One is more general. How do we manage for old growth without creating mapped areas? Is there a recognized ratio of old trees to open space to clumps that everyone agrees on? Similarly, another asker asked, in a more specific example, in a stand of mixed Ponderosa, Doug fir, and larch, what should be the spacing from old Ponderosa pine if there is also Doug fir and larch present?
I'll take an initial crack at it. If you take a look at Derek Churchill and others' implementation guide, what they do in each geographic area is they'll very often go out and they'll sample with very large plots the forest conditions and develop reference conditions for specific forest types and fire regime areas that allow them to be able to then take their established marking guidelines that are relevant to a particular geography. So I really urge you to take a look at the implementation guide. And essentially what they're doing is they're sampling tree clump and gap size distribution within a geographic area to give them insights into what was normally occurring and how variable that was. And then they try to replicate those conditions.
Great. Anyone else want to add anything? Or jump to the next one? All right. How much do these ideas apply to even-aged lodgepole pine stands, say on cold soil sites?
I'll sort of start and then other people could jump in too. I think that the answer to that question really depends on the landscape you're in and where that lodgepole stand is. So lodgepole is a species that has an enormous range of environments it can live in. And so just for example, in central and eastern Oregon, it can be found in high elevation forests on steep slopes that are super cold environments, or it can be found below the Ponderosa pine sites in really flat basins in a much drier environment where it was surrounded by frequent fire. And so what you see in lodgepole forests in different contexts are very different development and fire histories. So it's a very flexible species and it depends on where you're at.
I think it'd be great to make just a brief plug for Trent Seeger's work in lodgepole. What we think of today as lodgepole in cold air drainage areas in some of these systems in Eastern Oregon, but that were historically aspen stands when there was fire on the landscape. And I think the Nature Conservancy has done a good job of summarizing that work, correct?
Yeah, I think one thing, the issue you're pointing out is there's lots of riparian areas and meadows that historically used to be aspen systems and willow systems, and the removal of fire in those areas has actually converted the area into a lodgepole forest, where a lodgepole forest didn't occur before.
We're also seeing in some of our research in Bob Marshall Wilderness that fires of all severities have occurred historically in lodgepole pine. And as Andrew said, it really depends on where you are and what the fire history has been. For example, in some patches in the Bob Marshall, we will see a grass sward underneath open canopied lodgepole pine that had been reburned 2 or 3 times. And in the second and third fire, the former forest was consumed. And so you would see lodgepole obtaining again, but you'd see trees with 2 to 4 fire scars on them, even thin bark lodgepole pine. So it's not out of the realm of possibility that lodgepole pine, depending on its disturbance history, can experience lower severities. But it's not the routine. More commonly, we see high severity fire or moderate severity on the high end being impactful in large areas of lodgepole pine. And in the average active fire regime within an extensive lodgepole area, you would see patchiness of burned and recovering lodgepole patches being the significant feature of the landscape of an active fire regime. And you take fire out of those woods, and what you see is lodgepole pine develop in continuous forest cover, and densities increase and so forth. So the historical patchiness of lodgepole pine cover was more often than not derived from these high and moderate severity fires. And very often 30 to even 50% of the landscape would be in burned and recovering condition.
Great. All right, we've got a number of different questions asking about weighing the trade-offs between carbon storage on the east side and removing biomass through forest resiliency treatments.
I'll take a stab at that. I don't think that there is a correct answer. I'd love to hear from Keala. First of all, as one of my slides indicated, there's far less carbon storage potential in these dry east side forests than in the moist west side forests. We know that there is probably a magic number in terms of how much these dry forests can store reliably, but that number is probably only meaningful at a landscape scale. And there's probably lots of ways to get there with fire, thinning, et cetera, et cetera. I don't think that there's a correct answer. Keala, what do you say?
Thanks for the handoff.
It's highly likely to me, given the mortality we've observed out in Eastern Oregon, that our dry old growth forests are rapidly turning from a carbon sink to a carbon source. We know that that's happened in dry old growth forest of California. They're hemorrhaging carbon to the atmosphere far faster than they're storing carbon. And given the drought and fire situation that we're facing looking forward, it's almost certain that that's what's going to happen to Eastern Oregon forests too. So I don't think even optimizing carbon storage is really the name of the game. I think it's all about stabilizing the carbon that's there.
Absolutely agree. Go ahead, Keala.
Just saying that was exactly the point I was going to make. Stabilizing carbon is the name of the game in these forests, especially, as James said, given the uncertainty about future impacts of climate on disturbance interactions, and impacts of climate on the capacity of these systems to regenerate after disturbance.
The reference for land sector carbon stocks associated with forest is likely the reference associated with an active fire regime and an active fire regime under climate change, and rather than, you know, areas where forest had accumulated and become dense prior to the shift in the climate in the 70s, 80s, and 90s of the last century. If you stop and think about the punchlines of the talk that I gave, I basically said that the landscapes had stabilizing feedbacks that were negative feedbacks to severe fire. And when we remove those stabilizing feedbacks, like James said, we destabilize the landscape. If we're going to create fire and climate adapted landscapes, it means restoring at multiple levels, stabilizing feedbacks. And that means less forest in order to produce metastable conditions, conditions that don't oscillate quite so much. So less is going to be more carbon.
Great. I'm wondering if the panelists can speak to the overlap between commercial logging that is done on Eastside and ecologically focused thinning. Is there something needed to be done to promote a market for restoration byproducts?
The difference is really significant. If you stop and focus on the trees that have encroached during the period of fire exclusion, we're really talking about the lower crown classes that are contributing fire intolerant trees and significant fuel ladders to the older trees. So low thinning, variable density thinning treatments are going to be critical in those species. And that contrasts significantly with the large tree removals of the 20th century, where the trees we're talking about retaining were preferentially removed. So yes, there's a tremendous need to do restoration thinning and to have infrastructure that's supportive of that. And it's very, very different cutting methods and so forth.
Great. Someone asked, what is appropriately managed fire? And they asked in part in response to yesterday's call from the Chief of the Forest Service to suppress all fires for now.
Isn't that special?
All right, I want to cut you off, Paul, before you lose your pension. I'm joking, of course. A certain number of fires are going to escape control. A certain number of fires are going to escape control. Has always been that way, will always be that way. There's ways to stage fire suppression resources more effectively. We can throw more money and people at that issue, but there are going to be fires that escape control. That's the memo from Mother Nature, which trumps the memo from the Chief of the Forest Service. We don't have a choice about whether to have fire. We have a choice about having fire under moderate weather conditions, or we have a choice about whether to have fire under extreme weather conditions. And the choice to try and suppress all fires is really a choice to have fire during extreme weather conditions.
Thanks for saving my pension. I was going to go in another direction than you thought. There's a lot of debate right now, and it's really volatile, not just within Fed agencies, but really across the board, about the role of managed wildfire. And as you know, a letter was circulated from some of our colleagues basically expressing their concern about application of managed wildfire. And I think our new chief is basically saying, let cool heads prevail. Let's take this in, give ourselves the free space to be able to discuss it and I think that's what's happening because we're at a high level of preparedness right now. He's basically calling for that not being the case in application with the current fires and the current fire season. But I think he's creating free space to have that dialogue internally and externally and so forth. So I think that, as James said, Mother Nature is basically suggesting that fire and smoke are largely in our future, and we get to choose how we want it. Do we want to apply it, or do we want to just take it as it comes? And I think that we've got an opportunity. It's a big gray area between just take it as it comes and do nothing. And I think we're going to seriously explore throughout Western North America ways to be able to occupy that gray space in between more intelligently and at larger scales. See, James, I kept my pension.
Yeah, I think you put it better than me, Paul. Thanks.
All right, the next question is, can the panelists speak to the differences for wildlife between old growth clumpy stands and overstock stands?
No,
Yes.
I'm not a wildlife biologist. Obviously different habitat types have different habitat potential. Dense stands are great habitat, for instance, for elk to cool down in the summer months. They're less capable habitat for rare forbs that need a lot of light to thrive. I think we could, and I think people have written books about all these different trade-offs. Gail.
Actually, Derek Churchill and Trent Seeger have a document that's in preparation, and I think we should put some pressure on both of them to get this, the ecological impacts of ICO out so that the public can enjoy the insights they've gained over time. I'd also extend this question to say, what are the wildlife impacts of the overstocked forest that existed before the Bootleg fire and exists now after the Bootleg fire, and the conditions that exist now after the Bootleg fire?
An awful lot has been written about various species. And one of the things that I take home from the wildlife literature, where it concerns changes in landscape patterns and the dominance of different successional conditions, is that there are winners and losers that are associated with it. And the message is, it really depends. White-headed woodpecker is currently a sensitive species, and it frequented many of the stand conditions that Kayla and Andrew and James discussed, because they were open ground conditions with all sorts of dead top pines and snags, where you'd see woodpeckers consistently creating and occupying cavities on that landscape. And so when you see those conditions really change significantly, you see a significant loss to certain populations of cavity excavators and secondary cavity users, for example. And I think when you go right down the line, you find out that there are winners and losers. And when you look at fire regimes and the domains that they historically occupied, you see guilds of species that also seem to travel with them. And when there are changes in the conditions, you see changes in the guild. And I think that's an awful lot of what I read in that literature now.
I think maybe one takeaway for me, and this isn't directly the question that was asked, but when we move to much bigger patches of higher severity disturbance with much longer timescales between them, we're taking these habitats and we're making them happen all at once. So before the Bootleg fire, we had a lot of closed dense forests over a really, really large area, providing essentially one type of habitat, and it's burned up, and that will benefit species, some species, and harm others, but it's happening all in one big chunk instead of being spread out in smaller patches and better distributed through time. So there's winners and losers, but there's also this aspect of providing habitat more evenly in time and space when we have more active fire regimes.
Great. Can the panelists comment on in what circumstances, if any, would it be appropriate to remove large but young Doug fir in order to maintain and protect old Ponderosa pine?
I think the simplest and best answer is that that's appropriate when those Douglas fir are, threatening the sustainability of those old growth trees. And it is often the case that, they're taking water resources away from those old growth trees and making them more vulnerable to the synergistic effects of drought, insects, and fire. Paul probably has some other helpful guidance.
I think that covers it. They change fire behavior significantly and resulting fuel loadings. And so when you see that the nexus of those things occurring in a stand, it suggests that those should be targeted with methods that allow you to create the openings and the fuel conditions that support the active fire regime.
Great. In California, Oregon, and Washington, there's had recent legislation that includes increased funding for both wildfire suppression and forest restoration treatments. If you could provide these state agencies advice about how to prioritize use of these resources, what would that advice be?
Prioritization is a matter of goals and objectives. If your goal and objective is to, for instance, protect communities from fire, then that obviously suggests prioritizing the space around human communities. If the goal is protecting old growth habitat, then you obviously want to prioritize, treatments in and around old growth habitat. If the goal is protecting municipal watersheds, then it's municipal watersheds. There's a lot of values at stake, and hopefully in the future, there's a political will to make investments commensurate with the need. In the meantime, yeah, we have to prioritize, and that's a question for society and for stakeholders, where those resources go.
I would just add that some of those, as people know well, some of those goals and objectives overlap. So protecting, we might extend it to protecting forest cover in places where we think forest cover will persist into the future, and that could potentially impact things like air quality and or water quality, for example, or cultural resources, or
Great.
I was just going to say one thing, that it's interesting that that question implies that we do need both, that we need all of these tools to move forward, which I think is a good message to have.
Great. We're in our last couple of minutes, and we haven't had a chance to ask all the questions, but I will be sharing a lot of information in the wrap up, as well as contact information for the presenters. But in closing, I guess I want each panelist to share what, if everyone had one or two key takeaways about old growth on the east side from this presentation, what would you want it to be?
Let's go in the order of the speakers. James?
honestly don't have anything to add. I'd just love to hear more from Andrew, Kayla, and Paul. Thanks again, everyone, for having us. And as I said, please drop us a line via email with some more questions or feedback. I really appreciate it.
I don't think this is directly a takeaway from the presentation, but maybe from the past couple of weeks of thinking about the bootleg fire. And we often think about restoring fire as, well, we're going to do that because we need to remove fuels, and it's all about fuel reduction. And this week I heard it's more about restoring resources and maintaining resources, and I think that's a really important message. And you know, at least the early results from that fire show that where fire had been put back into that landscape, there was a much better outcome. So for me, my main takeaway is hopefully we can put the right type of fire back into our dry forest as quickly as possible.
At the risk of stating the obvious, I just reiterate that the replacement time for large young trees, maybe centuries or less, but for old trees, it's multiple centuries if it's even possible under current conditions.
The more I read and understand what indigenous cultural burning practices were like and the rationale behind them, the more I'm in awe of how across North America cultures learned to live with wildfire at millennial time depths. They knew that fire and smoke were part of the picture, and they hedged their bets and lived safely by living with fire, cultivating the prescribed use of fire, and intentionally burning the landscape so they could have those resources and values. And I think there's a big takeaway from that experience of learning how to live peacefully with fire on the landscape, and rather than having sort of heavy-handed engineering solutions constantly trying to triumph over fire, learning that it's inescapable that fire will be on the landscape in large doses. How do we make that happen so it's not scary culturally, and we can do that successfully? How do we get the right kind of fire in the landscape so we can live with it? For me, those are the compelling questions.
Great. Thank you. All right. That about does it for time, though we will have some networking time after. I want to thank all of our panelists today for their presentations. I'll be setting up the breakout rooms here in a second. I want to plug our upcoming webinar in September, where we're going to move from Eastside to Westside and look at some great science happening and co-production opportunities around Westside specific fire with the Pacific Northwest Research Station. This will be posted to the web on YouTube coming up soon, and you can see that, go to that link for our previous workshop videos. And thanks again, everyone.
Thank you, Jenna and
Thanks,
Sally,
Jenna,
for all your work. Really appreciate it.
Thank you very much.